Okay, this is chapter 6 on jet aircraft performance. I'm going to highlight the important parts. Chapter 6 and Chapter 7 are both on jet aircraft performance. Chapter 7 is on applied aircraft performance, which will follow this. What we're talking about here, going to shift gears a little bit. This only is applicable to turbojet or turbofan aircraft, not propeller-driven aircraft. That's going to be in the next two chapters, 8 and 9. So make sure you are looking at it with that that type of context. The first thing I want to point out is on page 80. What you'll see here is a T-38 thrust required drag curve. You can look up a T-38. The Air Force uses them and NASA uses them as jet trainers. They're a pointy jet. But anyhow, if you look at this thrust required, you'll see thrust required on the left side, and then velocity down below. You'll see the Buffett limit, and you'll see L over D max. And at L over D max, we learned this from drag, that's where minimum drag is going to occur, so that's going to give you the highest lift to drag ratio. And then you'll also see the Buffett limit there, which is, in this airplane, is going to be thrust required 2,000 at about 150 knots is where the Buffett limit is, and your L over D is a little less than 1,000 thrust and at 250 knots true airspeed. So this shows thrust required curve for a 10,000 pound T-38. This is at a clean configuration on a standard day. Just said that thrust has 2,000 pounds at 150 knots. And then at 485 knots, also at 2,000 pounds, you can see minimum drag or thrust required occurs. Leftover drag, which is at 240 knots for this aircraft. So they say 240 knots to 250. So just make sure you can understand how to read this this figure. This is figure 6.2, and then read that first paragraph on page 81, and that explains the figure there on 6.2. Alright, the next thing I want to look at is figure 6.3. I'm going to draw this. So this is Q, V1, V2, and thrust acquired. I'm sorry, thrust available, not TR. So TA is thrust available. Q is mass airflow. V1 is inlet velocity, and V2 is exit velocity. So we can write this equation as thrust available is equal to the mass airflow times V2 minus V1. So this is an equation you're going to need. The next thing we'll look at is propulsion efficiency. And we write that like this. And it's going to be equal to 2 times V1, which is the inlet, divided by V2 plus the exit plus this, and this is going to give you propulsion efficiency. Propulsion efficiency is important because what this can drive a 2 jet engine configuration instead of a 1. And that's where propulsion efficiency is important. You'll see there another equation for thrust available turbojet aircraft, so they just rewrite it. It's on page 82 for density area times velocity 1. So they basically take mass airflow, which is equal to density times area times velocity, inlet velocity. and times the exit velocity minus the inlet velocity. That's halfway down on page 82. Next thing we'll look at is fuel consumption. This is on page 83. It's going to be equal to fuel flow divided by thrust. This is in pounds, and this is in pound hour. And this will give you your specific fuel consumption. And then if you want to know what total fuel flow is, it's going to be equal to T times CT, which is fuel consumption. All right. Let me see here if there's anything else that was important I wanted to point out. Figure 6.7 on page 84. Shows you fuel flow versus altitude. So you can see fuel flow decreases, right, with altitude. And then you can see the temperature plot as well. So these jet aircraft performance charts, really what they're important is making sure that there's thrust available for the various phases of flight. You know, at maximum drag, minimum drag, clean configuration, dirty configuration, whether or not we need one jet engine or two jet engines, how big the engines need to be. That's all the importance of these types of calculations. The next thing I want to talk about is rate of climb. And we're on page 89. So if we draw this, this one's going to be max. Oh, if I can write. Max climb. So hard to write on this sometimes. Max climb angle. And max rate of climb. So this is very similar that you're used to, Vx and Vy, right? So for a jet aircraft, rate of climb is going to be equal to 101.3 times the velocity in knots times thrust available minus thrust required divided by weight. And this is in feet per minute. So there's the equation for rate of climb for a jet aircraft. Page 90, go ahead and take a look at that. One of the important parts here on page 90, it says for jet aircraft, we've seen the following items of performance occur: L over D max, minimum drag, maximum engine out glide range, maximum climb angle, and maximum endurance. It should be obvious that it is important to know the airspeed or angle of attack for L over D max. Airspeed will vary with aircraft weight, but angle of attack will not. Indicated airspeed for L over D max will not vary with altitude. And you can see that in the charts here on page 91. The book continues to talk about total range of aircraft and specific range. I'm not going to get into that. I don't think it's really important right now. So I just want you to get a feel for basic jet aircraft performance. And this concludes Chapter 6. Thank you.